Everyone we'll look at today is this idea of electric fields a little bit more, and we want to be able to calculate the electric fields at different points in space. Electric fields exist everywhere as long as a charge is present. To test the field, remember we're using a test charge which we called positive, and that positive tells me where the field is going to point. The field is a vector, and the test charge will feel a force in the direction of the electric field. Remember, the test charge is positive, so positive charges will feel a force away from the electric field. Negative charges will do the opposite. Negative charges will go against the electric fields because, like we talked about a little bit today, if we have an electric field and the electric field points towards the right and we put a positive charge in there, that positive charge will feel a force in the direction of the field. Well, why will it feel a force in the direction of the field? Well, since this field is so strong and we're only looking at a specific region, over here to the left, there must be some large positive charge. I can't see it, but I know that the electric field lines originated from the left. And they're heading towards the right, so way off screen to the right must be a large negative charge. So that's how I know where the positive charge wants to go. It's going to get away from those positives and try to get towards those negatives as quickly as possible. Electrons, on the other hand, don't want to go anywhere near those other negative charges. So electrons feel a force against the electric field, and they accelerate in the opposite direction. So that's the big difference between gravity and electric fields here. In electric fields, they show you where positive charges want to go. But since there are negative charges as well, the negative charges will go against your field. And you can see in that table there's some common electric fields found in nature. So household wires have small electric fields, while talking about lightning bolts, we're talking about electric fields up into the 10,000 newtons per coulomb range. So they're very, very strong, but the strongest ones are between the electron and the proton in the hydrogen atom. So looking at this, we can see that finding the electric field from point charges, like we showed yesterday, is kq over r squared. So you take Coulomb constant, the charge you're interested in, and r is the distance from that charge. And that's all you need to know. So what we have down in this drawing here is we have a positive and a negative charge. You can see that E1 is coming from the positive charge, and E2 is coming from that negative charge. So in region 1, the negative is trying to pull it in, and the positive is trying to repel it. In region 2, both electric fields point in the same direction. That's because the negative is trying to pull to the left, and so is the positive. And in region 3, we see the fields are fighting each other again. Now you can get to the point where you find electric fields do cancel. So here's what we got. We got a positive charge. We'll give that positive charge a +1 microcoulomb charge. And that negative charge, let's make it -2 microcoulombs. So the question is, where would the electric field equal 0? Well, first thing you need to do is figure out what the test charge would feel in different regions. I would put a test charge, say, between those two charges, and the negative charge is going to attract it in, and the positive charge is going to repel it. So right there, the two electric fields are pointing the same way. No cancellation. Let's try somewhere over here. Over here, in this region, I can see that the electric field from the positive charge is going to push away, and the electric field from the negative charge is going to pull in. So there might be cancellation over there on the right, but that negative charge is really strong, and we're a little bit closer to it. What if I went over here on the left? If I moved over to the left of that, or the positive charge, I would see the negative charge trying to attract it, and that positive charge trying to repel it. So let's pick this region over here on the left to be our place of cancellation, where E1 is going to equal E2. And if that's the case, if I want electric field 1 to equal electric field 2, I can say that electric field 1 is kq1 over an x distance away from the positive charge over. The second charge is kq2, and the distance there is 1 meter plus that x distance. So 1 plus x squared. You can see in my two equations there, I have a K constant, and that's really the only thing that can cancel out. So the electric field from charge 1 is Q1 over x squared, and the electric field from charge 2 is 1 plus x, and we square that whole quantity. Go ahead and solve this. Your roots, when you finally get your answer, should be something like this. You should get an x of negative 0.41, and you'll get a root of positive 2.414. So there's actually two locations where the electric field is going to cancel. Negative 0.4 meters to the left of that positive charge, but also 2.41 meters to the right of the negative charge. So right in that location. So these two roots do make sense and they are real. But what if we didn't worry about just cancellation? What if we wanted to know just how strong the electric field was at certain locations? So taking this, we've got two positive charges, one at 8 nanocoulombs and one at 12 nanocoulombs, and you can see the distance markers down below. So they've got two locations there. They've got location A and location B. Let's calculate the electric field strength. So charge 2 is 3 meters away, and charge 1 looks like it is 7 meters away. Now you can see that electric field 1 and electric field 2 are pointing in the same direction, so I just have to use KQ over R squared and add the two electric fields I get in the end. When you do that, you should get around 13.4 newtons per coulomb as the electric field strength. What about that location B? Well, location B, you're going to do the same thing again. Do KQ over R squared, except you have new distances. Charge 2 is now only a meter away, and charge 1 is 3 meters away. Putting in those values for the electric field strength, E2 ends up being 107.8 newtons per coulomb. And if you do the electric field strength for E1, E1 ends up around 7.98 newtons per coulomb. So the electric field from charge 1 is a lot weaker. 1, it's a smaller charge, and 2, it's further away. You're closer to that Q2, so that field is much stronger. So I'm looking at those two fields. I see the arrows are pointing against each other. So my net electric field is the combination of these two. And you should get around 99.9 newtons per coulomb. That's what we can do in these different locations. We can use the electric field equation to find the strength of the field, but all that tells us is how strong the field is. It doesn't tell us anything about forces. So you can use the definition of electric field as force per charge to find the force on, say, an electron that finds its way into that field. So if I put an electron in the electric field at location 2, I know the electric field strength is 99.9 newtons per coulomb. If I want to calculate the force, just multiply the electric field by charge. I get an electrostatic force on the electron of 1.6 times 10 to the negative 17th newtons. And from that you could calculate accelerations of that electron, but the direction, where would that electron want to go? If I put an electron right here at that 2 meter mark, that electron's going to want to find its way to the plus 12. It's feeling more attraction to the plus 12 than the plus 8. Our net electric field was negative because it was more electric field to the left than right. And that's exactly where a positive charge would go. A positive charge would feel a force to the left. Electrons go against the electric field and would head off to the right. What happens when we pick a location that's not along the x-axis? Picking that location 3 meters above those two charges. Well, nothing's going to change here. To calculate electric field strength, you're going to do K, Q over R squared for each charge. Once you've got the magnitudes of those vectors, then you need to break them up into its components and solve for the net electric field. I'll give you what electric field 1 and electric field 2 equal. Electric field 1 is 798 newtons per coulomb upwards. Electric field 2 is 4.31 newtons per coulomb. So I know the field strength and I can get my angles by using some trigonometry, and combining the x and y components will give me the net electric field. I can see I've got two electric fields going up, so I'm going to add those, and only one electric field heading to the left. So I'm going to have a leftover x component and a combined y component. So the net electric field will point up in that direction. And if I put a positive charge in this field, the positive charge will feel a force in the same direction. The electrons would feel a force against that. So calculating electric field strength and magnitude are just like calculating electric forces, except you only have to worry about each individual charge. Once you get the net electric field, we can then find forces on our protons and electrons or whatever charge may be in that region.